Welcome to the first section of Chapter 9 for Math 141 Statistics at Morton College. I am, as ever, your instructor for this course, Dr. Scott Spaniel. Today, what we're going to do is start working on section 9.1. So this is what we're going to talk about in Chapter 9 is confidence intervals. So a confidence interval is simply an interval that you put around a sample mean or proportion that we talked about in Chapter 8. Because when you are looking at sample data, you're very rarely, unless you get absolutely just really lucky, going to get the same number that you would get for the population. And when we collect sample data, what we're trying to do is we're trying to get an estimate for the population. So confidence intervals are one way to do that. So what we can do with a confidence interval is we can say, okay, well, we think 70% of people like to watch sports from our sample. But we're going to give it a range around that of plus or minus 3% because we're not sure where the population actually is, but we know it's in that ballpark. And the ballpark, the range, is determined through a number of factors that we'll talk about in these sections. So in section 9.1, we're going to start out looking at doing this for proportions, like the percentage I just gave you. The most common ones you'd see of these are polling data, whether it's about an individual question or as is could be currently coming up. It is right now while I'm recording this presidential election, and they give you polling data from different states and nationwide, but they always give it to you with a margin of error, and that's what we're going to look at. So if you take out, if you want to follow along in the note sheets, you can take out the Chapter 9 note sheets that will look like this and are available on either Blackboard or in my math lab, and we can start talking about them. So estimating a population proportion. So the first part of any confidence interval, when we're estimating it, is a point estimate. Okay, this is a single value of a statistic that estimates the value of a parameter. So this is things like x bar, p hat, okay, are good examples of point estimates. Then what we do is we can create confidence intervals. So a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So it's an interval of numbers that are around a point estimate. The level of confidence represents the expected proportion of intervals that would contain the parameter if a large number of different samples is obtained. The level of confidence is denoted 1 minus alpha times 100%. Okay, where alpha, I think I mentioned this later, but I'll say it now, where alpha is the proportion of the samples that won't be in the confidence interval. We can write confidence intervals in basically one of two ways. We can write them as a point estimate plus or minus the margin of error. This is the most common way you see them reported, especially in the news media. Or they can be as a lower bound and an upper bound. So they can be a range of numbers where they would fall, an interval of numbers in which the parameter should fall. A 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. So for example, if I was doing a 95% confidence interval, that means that 95% of all the possible samples that I make a confidence interval for should have the parameter in it. And by that token, 5% won't have the parameter in it. So one of the key takeaways here is our goal is to be as confident as possible, but we're never going to be 100% on these. There's always a chance that our sample is one of the ones that doesn't have the parameter in it. Z sub alpha is called the critical value of the distribution. It represents the number of standard deviations that the sample statistic can be from the parameter and still result in an interval that includes the parameter. In general, for confidence intervals, because we're doing an interval of values and there are values on the outside on both sides, we usually do it as z sub alpha over 2. But a critical value in general is just z sub some area that is outside of our data value. So these are based on the sampling distributions of p hat and then in the next section of x bar that we talked about in chapter 8. So for a simple random sample of size n, the sampling distribution of p hat is approximately normal when the following things happen and has a mean of p and a standard deviation of the square root of p times 1 minus p over n, provided that n times p times 1 minus p is greater than or equal to 10. Okay, so that's one of the things we talked about in the previous section, that these things were approximately normal if n times p times 1 minus p is greater than or equal to 10. The other thing that's important is it's required that each trial be independent. And in order for that to happen, we need our sample to be small compared to our large population. And the general idea here is that the sample size can be no more than 5% of the population size. So in notation, that's lowercase n is less than or equal to 0.05 times capital N. In practice, in most situations, this will occur because, especially when you're talking about most of your populations you're going to be looking at are like all 19-year-olds in America. That's a giant number of people. So if you only survey like 1,000 of them, that'll definitely be less than 5%. So in most cases, this will be the case because you'll be looking at very large populations compared to fairly small sample sizes. The way you calculate these is as given here, but we're mostly going to do this with class calc, so you don't need to worry about these formulas too much. But in general, the idea is you have a lower bound and an upper bound. And the lower bound is equal to the point estimate minus the margin of error. Okay, this is the margin of error, which can be noted E. And same idea here, point estimate plus the margin of error. And notice the margin of error is simply the critical value, the number of standard deviations away from the mean of times the standard deviation of the problem we're doing. So we're multiplying the number of standard deviations we want to be from the mean times the standard deviation of that problem. Okay. And once again, notice we need to be, for this to work, these two things have to be true. N times p hat times 1 minus p hat has to be greater than or equal to 10, and n times n has to be less than or equal to 5% of capital N. So let's practice this with some basic numbers. So we've got a proportion here. We have an X value. 400 people in our sample have the characteristic out of 1,200 total in the sample with a confidence of 95%. So let's look at how this works in class calc. So in class calc, we're going to go to stat, and now we're going to go to tests. Okay, so this is under tests in class calc. And then what we want to do is we want to do one prop z int. Okay. So 1 means one variable, prop means proportion, z means that we're on the standard normal curve, which we are here, right? Because we're using z sub alpha over 2, and then interval for confidence interval. And then all we have to do, and this is why these are fairly easy to use, is enter our x value, our n value, and our confidence level, the things we were given. Now, the one thing to note here is, so if I put in x is 400, n is 1,200, and then if I try to put in 95%, it doesn't like that. So what you have to do is you have to put it in as a decimal. And there's all my answers. And it actually gives me pretty much all the things I could possibly want to know about this, right? It gives me my interval. So my interval here, my lower bound is 0.307, and my upper bound is 0.360, and my margin of error is 0.027, and my p hat is 0.333. So it basically gives us all the values, all the things we could possibly want to know about this. Okay. One other thing, you could write this lower bound, upper bound in what's called interval notation if you wanted, which would be 0.307, comma 0.360. Okay. But that's the idea of what we're looking for here. Okay. Now, one of the interesting things we want to look at is, well, what happens to the confidence interval if we decrease the level of confidence and increase the level of confidence? So let's try decreasing this to 0.9, and let's see what happens. So if I'm less confident, notice now, so a 90% confidence interval is 0.311 to 0.356. And then let's try a higher one. So let's try 99%. So that gives me 0.298 to 0.368. And so what we can say is that if we are less confident, we get a smaller interval. So if we'd like a smaller interval, we have to be less confident. If we want to be more confident, we have to have a bigger range, right? If I'm trying to guess, let's say I'm trying to guess the number of wins the Cubs are going to have in a season, I want to have a big range to make sure I get the answer right. Okay, if I want to be more confident in my answer. But if I'm less confident, if I want to pick an exact number, I just won't be very confident I'm going to get it right. The other thing that I didn't put in here, but that can change our confidence level, our intervals, has to do with the sample size. So let's see if I change these values. So if I just double both of them. So let's make that 800 and make this 2400. So notice p hat is exactly the same, but what do you notice about these values? Well, they get a little bit smaller. They get actually much smaller. If I double the sample size, what I get, so now this is with n equals to 2400, I get 0.309, comma 0.358. And this is still with 99% confidence. So what you should notice here is as I increase the sample size, the confidence interval got smaller as well, right? The bottom number got bigger and the top number got smaller, so they got closer together. So another way to be more confident in your answer is to have a bigger sample size, which should also make sense, right? The more people you ask, the more likely your answer will be closer to what the population is. Okay, so that's the idea of how this works. So now let's look at an actual application problem of where we could use this. Okay, so on the next page, I should probably eventually get some newer problems here, but anyway, we'll use this one from 13 years ago. So in USA Today Gallup poll conducted November 2nd to the 4th, 2007, 768 of the 1,024 randomly selected adult Americans aged 18 or older stated that a candidate's position on the issues of family values are extremely or very important in determining their votes for president. Obtain a point estimate for the proportion of adult Americans aged 18 or older for which the issue of family values is extremely or very important when voting for president. So if you want to do this by hand, this is something we talked about in chapter 8, which is that p hat equals x over n. So in this case, that's 768 over 1,024. Okay. So we can do that pretty easily. Hopefully. Which is 0.75. So there's a point estimate. But we could also just use class calc to do the confidence interval, and it's going to give us that answer as well, right, as we just saw. It gives you p hat. So verify the requirements for constructing a confidence interval are met. So let's remember what those are. So the first one is that n times p hat times 1 minus p hat has to be less than or equal to 10. So in this case, that would be 1,024 times 0.75 times 1 minus 0.75. Okay, so that's 192. So that's plenty big enough to use this. And then the other one is that n has to be less than or equal to 0.05 times capital N. In this case, we don't know what the size of the population is, but it says all adult Americans aged 18 or older. So there's about 300 million Americans. Let's say half of them are adults, which would be still probably not enough, but let's say half of them. So that's 150 million. Okay, so in this case, and our sample was 1,024. So in this case, 0.05 times 150 million is 707. Did I add an extra zero? Would be 7,500,000. So we could have any sample up into including 7,500,000 people in it. So that's a lot less. So in general, like I said before, you're not actually going to have to actually do the math there. If your population is some percentage of like all Americans or some large subgroup of all Americans. So yeah, so we can do a confidence interval here. Okay, so once again here, I'll write here, we're going to do the one prop z int. That's what we're going to be looking for. So when we go into the calculator, I'll just you can type it out like before, or I'll just show you where it is again. You go to stat, tests, one prop z int, and then you just have to put in x, n, and the confidence level. So in this case, x is 7. Let me remember 768. N was 1,024, and our confidence level is 98%, so 0.98. Okay, so that gives us a confidence interval of 0.719 to 0.719 to 0.781. Okay, so that's a point 75%. If I want to write it as the point estimate plus or minus the margin of error plus or minus 3.1%. And then it says, is it possible that the proportion of adult Americans aged 18 or older for which the issue of family values is extremely or very important in determining their votes for president is below 65%? Is it possible? Yes, right? Because this is not 100% accurate. Is it likely? No, right? Because 60, it's not, so it is possible, but not likely, because 65% is not in our interval. I was trying to remember, did I forget to talk about something? No, I think I'm okay. Okay. So at this point, what I'd like you all to do is pause the video for a second. Oh, sorry, I didn't switch screens, so let's go back for a second. So it is possible, but not very likely. So that's what you should be getting for this one. So at this point, what I'd like you to do is flip over to the next page, pause the video, and try doing this problem. Okay, so now that you've all had a chance to try it, let's go through it together. So like I said, you can start off by getting the point estimate. So p hat is 604 divided by 1,010. So that's 0.598. And then you want to verify that the requirements for making a confidence interval are met. So that's n times p hat times 1 minus p hat. So in this case, that's 1,010 times 0.598 times 1 minus 0.598. Which is 242.8, which is a lot more than 10, so that works. And then is 1,010 less than 5% of all Americans? Yes. Okay, so we're good to go. So N would be less than or equal to 0.05% of N. Okay. And then they wanted us to make 2 confidence intervals. Okay, so we could do that here. So the first one, X is 604, N is 1010, and our first confidence level we want to be 95%. So that one, we get 0.568, comma 0.628. And then they want us to do the same thing, but for 99%, so put in 99. And for this one, we get 0.558, comma 0.638. So notice, for these, when we increased our confidence level, the interval got a lot bigger. In fact, it got 20%. It got 2 percentage points bigger. So we went from 56.8% to 55.8% and 62.8% up to 63.8. So it got 2 percentage points wider to be much more confident. So when deciding on a confidence level in this class, for the homework or problems will tell you what to use for a confidence level. But in general, you want to pick a confidence level based on which is more important. Having a fairly specific answer or making sure it's right. Okay, making sure it's definitely right. So it depends on how serious which one of those answers is. Now, in the examples we've done so far, I've told you what the characteristic is and what the sample size is. So what we want to practice real quick is, well, what if you have the raw data? Which I'm actually, since I started talking about it, I'll do this problem first, and then I'll come back and we'll talk about this one. So how do you make constructing a confidence interval for the population proportion from raw data? So the data set provided below contains the variable FO that was determined for a random sample of tornadoes in the United States in 2017. The Fujita scale is used to describe the range of wind speeds of a tornado. A tornado whose Fujita scale is 0 has wind speeds less than 73 miles per hour. The column F0 indicates whether a tornado had a Fujita scale of 0, yes or not, no. Create a 99% confidence interval for the population proportion of F0 tornadoes in the United States given using the given sample. Okay, so what you need to know in order to do this, right, is X and N. Well, one way to do that is by hand, right? Just go through here and count how many no's there are and how many yeses. So 1, 2, 3, 4, and so on. You can also use Google Sheets to help you do this. So earlier, I went ahead and put this data into Google Sheets, and what I want to do is I want to count these up, right? So the way I like to do is make 2 rows. So I've got my yes row and my no row. And then I can use a command called Countif. So I'm going to put in Countif. And then for Countif, you put in the range you want to look for. So in this case, we want to look in A. So I do A:(A). And then I want to know if it says yes. So there are 2 ways to do that. You can just type in yes in apostrophes, or since I typed yes into C1, I can just tell it to match it to C1. So if it looks like C1, count it. And so when I did that, it counted 20 yeses. And then if I want, I should just be able to pull this down now, and now it'll count no's, right? Because now if you look at this one, it says count if in A, it's C2, and C2 is a no. And then if I want the total, I can just add those together. So the total number of answers is just the sum of these 2 cells, D1 to D2, which is 50. And so that gives me the values I need. The values I needed was that I wanted to know, I'm looking at a confidence interval for the population portion of F0 tornadoes, so that means I want to look at yes. So X equaled 20. And then I also need my sample size, which was 50. So 20 out of 50 are F0 tornadoes. So now I can go to my Graphing Calculator app and use my confidence interval. 1 prob z int. Put in my X, which is 20. My N, which is 50. And my confidence level, which is 0.99. And it'll give me a confidence interval of 0.222 to 0.578. Okay, and that's all there is when there's raw data. So if you have a list of raw data, what you want to do is you want to use Google Sheets to count up how many of them there are of each type, and then that'll allow you to find X and N. Okay. So then the last question here was just pointing something out about margins of error. So back at the top of page 5. So the Gallup organization conducted a poll of 2014 likely voters just prior to 2004 presidential election. The results of the survey indicated that George W. Bush would receive 49% of the popular vote and John Kerry would receive 47% of the popular vote. The margin of error was reported to be 3%. The Gallup organization reported the race was too close to call. Use the concept of confidence intervals to explain what this means. So in this idea, right, the results of the survey say that George W. Bush is ahead. But we know that the answer most likely falls somewhere in the range of 49% plus or minus 3%. And for John Kerry, the most likely his actual falls between 47% plus or minus 3%. So that would give us intervals of 46% to 52% and 44% to 50%. And so the reason they would say this is too close to call is it's very likely that the actual number for George W. Bush is, say, 47%, and the actual number for John Kerry is 49%, in which case John Kerry would win. Okay, but it's also equally as likely that it's 51% for George W. Bush and 45% for John Kerry, in which case George W. Bush would win. So when confidence intervals in a case like this overlap, that's when they call it too close to call. Okay, so that's the idea there. Okay, so that's it for section 9.1. We'll hopefully see you back soon for section 9.2's video lecture, which will be very similar to this, except we're going to do it confidence intervals for means. But once again, we'll be using ClassCalc to do that. So if you have any questions about anything, please shoot me an email or a remind message. I'm more than happy to meet with you virtually anytime I'm free to go over how to do any of this, whether it's using the technology or talking about the statistical concepts. But other than that, I'll see you all next time.